Hello, hi. So last time we tied the ideas of the first chapter together with the ideas of the second and went through some topics at the end, the row space, column space, the fact that the dimension of the row space equals the dimension of the column space, and some other things that try to bring some of the ideas we are seeing together and connect sort of the old with the new. So naturally the check-in has to do with those ideas. So let's see if we how we do on these. So here's a matrix, a simple 3 by 3 matrix, and I'm observing that the first row plus twice the third, 1, 0, 4, plus twice minus 1, 2, minus 2, makes the second row. So there's some linear relationship among the rows of this matrix. It says find a basis for the row space, give the row rank, and then the second question is find a basis for the column space and give the column rank. So should be pretty easy. Let's give it a try. Okay, for our basis for the row space, all I have to do is Gauss's method. So I'm looking here at, let's see, 1, 0, 4, minus 1, 4, 0, and minus 1, 2, minus 2. And off I go with Gauss's method, row 1 plus row 2, and row 1 plus row 3. So I get 1, 0, 4 is unchanged, and I get 0, 4, 4, and then I get 0, 2, 2. And we spotted here that there's a redundant row. Minus 1 half row 2 plus row 3 gives me 1, 0, 4, 0, 4, 4, and 0, 0, 0. So the 0, 0, 0 shows me that there was a redundant row. There were no row swaps, so it was the third row was redundant on the first two. So that means that a basis for the row space is the first two rows, 1, 0, 4, and 0, 4, 4. And so the row rank is 1, 2. I can count to 2. The row rank is 2. Okay, and question 2 is not especially harder. For question 2, you want to know the basis for the column space, so you transpose the columns into rows, do row reduction, and then transpose them back. So you transpose first, and you get, if I did it right, 1, minus 1, minus 1, 0, 4, 2, and 4, 0, minus 2. Gauss's method proceeds in the usual way, minus 4 row 1 plus row 2, plus row 3, I'm sorry, excuse me, 1, minus 1, minus 1, 0, 4, 2, and 0, 4, 2. And again, a person spots that there is redundant, it was a column, but now it's a row. There was a redundant vector here, and so here we go, we take minus row 2 plus row 3, minus row 2 plus row 3, and 1, minus 1, minus 1, 0, 4, 2, 0, 0, 0. So the redundancy is perfectly plain. You get then a basis. I'm going to switch them back, transpose them back to be columns. So a basis for the column space is going to be 1 minus 1 minus 1, the transpose of the first row, and the transpose of the second row. 0, 4, 2. And so the column rank is 2. And of course, one of the theorems that we saw last time, a surprising theorem perhaps, is that the column rank and the row rank are the same, and obviously they work out to be the same. Okay, so a relatively straightforward check-in this time, or a relatively easy, straightforward calculation, but it tells us that the row rank and the column rank are the same. Reminds us that the row rank and the column rank are the same. Okay, well, very exciting. We're starting on a new day today, starting on a new chapter, and we're going to learn something sort of genuinely new. I think that for most people in this class, the kinds of things that we're doing in the third chapter are are something that they have never seen before, and so we'll go slow, go lots of examples, tons of examples, and some careful development, but it's always exciting to do something that is fresh. Okay, enough talk. Let's do. So let's see, isomorphisms it's called, and I'll start off by defining what an isomorphism is so that we'll know what we're talking about. So the basic idea is we have the intuition that the two tall vectors and the linear polynomials are the same in some sense, in that they're both two component spaces. So I'm sure that you have remarked to yourself that the vector 1, 2 is just like the vector 1 plus 2x in the respective spaces, and that minus 3 1/2 is just like minus 3 plus 1/2 x in their respective spaces. What makes these alike, what makes us able to say just like, is that the association is upheld throughout the operations. So for example, if I take 1, 2 and minus 3 1/2, that's just like 1 plus 2x and minus 3 plus 1/2 x. And same thing works for scalar multiplication. If I triple 1, 2, that's the same thing as tripling 1 plus 2x, or at least I get basically just like tripling 1 plus 2x. And similarly, I can link each two tall vector, not just 1, 2, but I can link each two tall vector with a linear polynomial. You just take the a and the a and the b and the b, and you think of them as somehow just like. Our job today will be to try to give a definition of what just like means. The important thing is that not only is there a connection between the left-hand side and the right-hand side, but that the connection holds, the connection continues to take place, the connection respects the vector space operations of addition and scalar multiplication. That if you add in the first vector space and you compare that to adding the associated things in the second vector space, why it's just like also. If you scalar multiply in the first vector space and you compare that to scalar multiplying in the second vector space, why it's just like also. And the technical jargon is that this association, this back and forth arrow, this association preserves the structure of the space. So the fact that we're studying linear spaces, the fact that we're studying vector spaces, linearity, means that we're interested in the structure. So of course, if we want to say just like, we mean just like in that the structure continues to hold. Just another example, because as I say, I think it's a new idea for almost everybody taking this course. So the two tall matrices, the 2 by 2 matrices and the 4 tall vectors are just like in that you can associate them in this way. If you had the 4 by 4, 2 by 2 matrix, 1, 2, 3, 4, you could associate that with the 4 tall vector, 1, 2, 3, 4, and you think of them as the same. So here we can think of these two as somehow just like, not equal, but just like. A person might say the difference is typographic. And again, the important thing of just like is that the association persists under addition or scalar multiplication. I couldn't fit scalar multiplication on the slide, so it's on the next slide. But association persists under addition and scalar multiplication if you add 2 by 2 matrices versus if you add the 4 tall vectors, the 4 tall column vectors. So addition of 2 by 2 matrices is just like addition of 4 tall column vectors, and this illustrates. And likewise, scalar multiplication of 2 by 2 matrices is just like scalar multiplication of 4 tall vectors. And this illustrates. Okay, so time for a definition, time to make it precise. And again, very sensitive to the fact that for many folks taking this class, the first time you see this definition will be like, what the heck is this? So we're going to do lots of examples, going to work through this at a deliberate pace. Okay. Isomorphism is the technical jargon here. Isomorphism between two vector spaces is a function. That back and forth arrow is supposed to denote a function that is a correspondence. So the function is 1-to-1 and onto. We're going to go again at some length into all these parts. You probably have heard, I'm sure you have heard the words 1-to-1 and onto in a calculus class, but we're going to go through and carefully describe how you verify these things. And also, number 2, preserve structure. That f of v1 plus v2 is f of v1 plus f of v2. So that's the preserve structure part that was on the previous slide for addition. And here's the preserve structure part on the previous slide for scalar multiplication. You see this symbol here, it's like an equal sign with a little twiddle written above it, so in some ways it's like a combination of equals and approximately equals. You read that as V is isomorphic to W. They're not equal, but they're just like each other. They're alike. And the function describes in what way they're alike. Okay, so again, sensitive to the fact that a person is typically a little at sea when they first encounter these kinds of functions. So one level of knowledge, kind of the base level of knowledge, is able to grind through some extremely routine homeworks, and I want to accomplish that base level of knowledge. So here we go. I'm giving you a how-to slide to get a person off the ground and started, and as we work through, we'll talk more and more about the concepts involved. But very first thing is, how do I do homework question sort of number 5? Okay, so that makes sense. So there are 4 things: to show that a function is one-to-one, to show that a function is onto, to show that a function preserves addition, and to show that a function preserves scalar multiplication. Of course, this was labeled item number 1 on the previous slide, the first 2. This was this was labeled item number 2 on the previous slide, the second 2. So to show that a function is one-to-one, you assume that you have vectors from the space, vector 1 and vector 2. You assume that f of vector 1 equals f of vector 2, and you go on to derive that therefore vector 1 equals vector 2. To show that function is onto, you take a vector, a generic vector from the codomain W, and you find a vector from the domain that maps to it. And again, going to do lots of examples of all this stuff. To show that a function preserves additions, we have to check that f of v1 plus v2 equals f of v1 plus f of v2. Lots of examples. And to show that f preserves scalar multiplication, we have to check that f of r times v equals r times f of v. Okay, so high time for an example, of course, but I'm going to keep referring back to the how-tos. Okay, so quadratic polynomials is isomorphic to R3. These A0, A1, A2, and A0, A1, A2, you think of those as somehow being associated. What does associated mean? That means there's a function which takes as inputs quadratic polynomials and gives as outputs 3 tall vectors, and it links the parts together. We think of the first part as being the first part, think of the second part as being the second part, think of the third part as being the third part. So this is the terminology for what I vaguely started off today with as a double arrow. This is kind of the technical way of saying the double arrow. And I can't overemphasize, whenever something seems too abstract to you, and there will be sometimes when you're working through this course when parts seem too abstract to you. Whenever something seems too abstract to you, extremely important, the key technique is to take out a pencil and put down some numbers. So A0, A1, A2, you're starting to say, what is happening here? Put down a 1, a 2, and a 3. Put down a 3 and a 4. And then you say, oh, well, you just take the constant term, you put it there. You take the coefficient of x, you put it there. You take the, okay, all right, I get it. And of course, that's exactly what the formula says. But you know, a person who is just learning their way through this doesn't have the capability of reading the formulas at a glance the way that an experienced person does. How do you get that capability? You write down concrete examples, lots of them. And then all of a sudden you start saying, wait, oh, no, that's actually easy. Okay, well, that's the good part. Once you say to yourself, oh, this is actually easy, good. You're on the other side of the divide now. You've passed through the gateless gate, and now you get it. Okay, so I have to check the 4 things from the previous slide. I have to check condition 1 and the condition 2. So to check that f is one-to-one, we're going to follow a do this kind of level, because that's where we are. To check that f is one-to-one, I will start off supposing that f of v1 equals f of v2, and I'll end up concluding that therefore v1 equals v2. So let's start in. F of v1 equals f of v2. So here's a member of the domain. Here's a member of the domain. The definition of f gives that you take the constant term and put the coefficient of the constant and put it there, coefficient in front of x, put it there, coefficient in front of x squared, put it there. Constant term, put it there, coefficient of x, put it there, coefficient of x squared, put it there. Now I have 3 tall vectors that are equal. Well, we know what it means for 3 tall vectors to be equal. It means a0 and b0 must be the same. a1 and b1 must be the same. a2 and b2 must be the same. And that gives me the conclusion I want, that a0 equals B0, A1 equals B1, A2 equals B2 means that the starting polynomials were the same. So in the how-to, back we go, there we go. In the how-to, you start off, you assume f of v1 equals f of v2, you do some thinking, and you conclude that v1 equals v2. That's exactly what I did. Next step, to show that f is onto, you pick a generic element of the output space. You can't take 1, 2, 3, it's got to be letters. You pick a generic element of the output space, the codomain, and you find what maps to it. You name, you exhibit what maps to it. Okay, here I go. So to show that f is onto, I pick a generic, this is not 1, 2, 3, 4, 5, 6. These are letters. Pick a generic member of the output space and you figure out who maps to it. Well, it's not hard in this case. Who maps to the output vector A0, A1, A2? And the answer is, of course, the input vector A0 plus A1x plus A2x squared. So for every member of R3, there's a member of poly 2 that maps to it. That's onto. Next, preserves addition, and of course preserves multiplication is going to be on the next slide. Preserves addition. Maybe I should go back and make sure a person looks at the how-to. Check that f of v1 plus v2 equals f of v1 plus f of v2, and then for multiplication it's going to be much the same. Okay, there's f of v1 plus v2. You see how the f parentheses are there and there? I put a little extra space to help your eye spot them. There's v1 plus v2 inside the parentheses. All the way down at the bottom is f of v1, see the parentheses there, match those parentheses, plus f of v2, and see there's matching parentheses. So that's what the how-to tells me to show, and of course there's some steps along the way, but the most important thing here is not the steps, they'll turn out to be very straightforward. The most important thing is understanding what you have to show. In fact, a lot of times when I solve these, I write down the beginning, I write down the end, and then it's kind of like a crossword puzzle. You say, how do I get from the start to the end? Okay, well, the way to get to the start, from the start to the end here is you add the vectors to add the constant terms, add the coefficients of x, add the coefficients of x squared. And now this is f of a single thing. See how the parentheses match there? This is f of a single thing. Well, what does f do? F takes the constant term and writes it on the top of the vector, takes the coefficient of x and writes it in the middle, takes the coefficient of x squared and writes it on the bottom. Down here, I'm going to need A0, A1, A2 because that's f of this, and I'm going to need B0, B1, B2 because that's f of this. So I need to get from here to here. Is that legal? Okay. Oh yes, it's obvious because that's how you do vector addition. Those two are equal. That's right. Okay, so step, 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 step. That's right. Done. The steps in the middle tend not to be hard. It's understanding the beginning and the end that tends to be the part where people say, I don't get it. What am I doing? So here, for preservation of scalar multiplication, I've got to show that f of r times a vector is equal to r times f of that vector. So there's the beginning, there's the end. I've got to get from there to there. Again, notice where the parentheses match. Open paren, close paren, right there. Okay, so inside the parens, r times a quadratic polynomial, you take r of the constant term, r times the coefficient of x, and r times the coefficient of x squared. That's how you multiply a polynomial by a real number. What does f do here? F takes the constant term and writes it on top. F takes the coefficient of x, writes it in the middle. F takes the coefficient of x squared, writes it on the bottom. Can I get from there to the... I need this because this here is f of a0 plus a1x plus a2x squared. So I need... Yes, that's absolutely right. That's the definition of scalar multiplication. That's how you multiply a vector times a real. Is you multiply the components times the real. So that's right. So I have equal, 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 so I'm done. So again, if you write down the beginning and write down the end, and sometimes I have the beginning and work as far as I can go, I have the end and work as far as I can go, and then I say to myself, can I make them match? Oh yeah, they do match. Good, I'm done. Okay, well this is the first time through for something that's tricky and that is brand new, not just a small twist on something you've seen before, but brand new. So two examples really. One example is not enough. Okay. So a second example. I have the 2x2 matrices that have a 0 in the lower right, and the 3 wide row vectors. and I'm going to define an isomorphism that's a little more abstract than the previous one. A, B, C, 0 is associated with, well, you take the upper right and you put it first. You take the upper left and you double it and put it second. And why do you do this? It's just an example. Don't get too excited about why you do this. It's just an example. I just want to show this is an isomorphism. First one was very straightforward. This one is slightly less straightforward. That's how you do examples. What do you put in the third slot? You take the upper left, add the lower left. Put that in the third slot. So as an example, 3210 maps to 264. And I'm going to verify. The how-to has 4 steps to verify. There's 1-to-1, person sees it on top. There's onto, person sees it on the bottom. There's preserves addition. There's preserves scalar multiplication. Okay, one at a time. And you might have a little trouble remembering how it goes. I'll flip back a couple times. For 1-to-1, what do you start with? What do you end with? You start by assuming that f of v1 equals f of v2. See it there? So f of a first matrix equals f of a second matrix. And you end by concluding that the two matrices are equal. There's stuff in the middle. I'll go through the stuff in the middle. But you start by assuming that f of the first equals f of the second, and you end by concluding that the first and second are equal. Okay, here we go. F of the first equals f of the second. Well, what's f of the first? F of the first is you take the upper right and put it first. You take the upper left and double it, put it second. You take upper left plus lower left, add them, put it third. Likewise over here. Well, let's see. Now I have 2 row vectors. b1 equals b2 is an obvious conclusion. If 2a1 equals 2a2, then a1 equals a2 is an obvious conclusion. Knowing that a1 equals a2, a1 plus c1 equals a2 plus c2 gives you that c1, and you're done. Onto. For onto, you start with a member of W. If you have scratch paper and you want to say to yourself, well, I'll try it with 1, 2, 3, and I'll try it with 4, 5, 6, and I'll get some idea of what to do, great, great, great. But that's scratch paper. When you go to actually give the argument, you have to use letters. So I often take out scratch paper and do it with numbers. That's how you make something concrete. Perfectly fair. But when you go to write down the answer, when, for example, you're doing the homework, when you go to write down the answers, you have to use letters. Okay, so here I go with letters. I have a 3 wide row vector, and being not a very imaginative person, I wrote x, y, z. I have to, remember the idea is to figure out what is the beginning and what is the end. So I write down a generic member of W, generic member of the codomain, and I've got to find somebody who maps to x, y, z. So down here you see I've found somebody who maps to x, y, z. Okay, so I have to find an input that maps to that output. Well, you know what, again, it helps to have scratch paper here. So remind yourself what happens from the previous slide here is that, remind yourself what happens from the previous slide is that the entry that goes first is simply the upper right. The entry that goes second is you double the upper left sort of stuff. So here we go. The entry that goes first see how there it is. I had a little trouble finding it. The entry that goes first is the upper right. That's what was called B in the previous slide. The entry that goes second, the middle entry, remember it said 2a? Well, so in order to get a y there, I need to start off with y over 2. And similarly, in order to get a z there, I'd have to start off with z minus y over 2 because you add those two together to get what goes in the third slot. It helps, again, to do this with numbers, but in the end, what you actually have to do is take out the numbers and put in letters. Preserves addition, same thing as the previous one, except it's somewhat more complicated with the a's and b's. You have to say f of first thing plus second thing. And you got to end with f of first thing plus f of second thing. This one I think is actually a little easier than onto. Onto is often the stumbling block. So how do you add two matrices? We know, of course, that you add the components. So this is f of that sum. So this is f of a single thing. What does f do? F takes the upper right and puts it first. F takes the upper left, doubles it, puts it second. And then f adds upper left plus upper right and puts it third. Okay, and how am I going to get to here? How am I going to get from here to here? Well, sometimes it helps to go backwards. So f of A1, B1, C1, 0 is this fella right here. Recognize it? F of A2, B2, C2, 0 is this fella right here. Recognize it? Does this? Yes, it does. These two are equal. As row vectors, the first component of this row vector is B1 plus B2. The first component of this sum, it gives you B1 plus B2. And like that. So if you put down the beginning and put down the end, and again, like a crossword puzzle, you say to yourself, how am I going to get from the beginning to the end? You work out the intermediate steps. Eventually you get better at it and you don't have to make such a big deal of it. But the first dozen that you do, half dozen or dozen that you do, you start saying to yourself, what do I have to do? So you put down the beginning, you put down the end, and you work your way toward the middle. Scalar multiplication is exactly the same deal. Put down the beginning, f of r times a member of the domain. Put down the ending, r times f of a member of the domain. And see if you can't work your way from the beginning and ending, work your way to making the two sides match up. Let's see, what do? So you say here, r times a member of the domain gives you this. Well, you multiply a real number times a matrix by multiplying the components. That's right. Maybe I'll go down to the bottom here and work my way up from the bottom. So r times f of a member of the domain. So f of a member of the domain is you take the upper right, put it first, upper left, double it, put it second, upper left plus lower left, put it third. So now I have those parts. Can I make them meet? Well, f of RA, RB, RC, 0 is indeed, you take the upper right, put it first, take the upper left, double it, put it second, take the upper left plus upper right, that's right, and put it third. And now are those two are equal. Done. So these steps often here follow in this kind of just sort of grinded out way. I will say that the onto often gives a person trouble, often gives me trouble, and the way to get onto typically is try it on scratch paper with 1, 2, 3. Try it on scratch paper with 5, 9, 12. If you do two of them with numbers and you figure out what maps to 1, 2, 3, and you'll figure it out. What maps to 5, 9, 12, and again you'll figure it out. Well, once you've figured out what happens with how to get backwards from 1, 2, 3 to the V, from 5, 9, 12 to the V, well, then doing it with letters turns out to be just, oh, well, you always do. And so that's the trick for onto. So the how-to gives you, back to the how-to here. The how-to gives you 4 steps to verify that something is an isomorphism. And of course, the homework consists of verifying that things are isomorphisms. The how-to gives you 4 steps. To show the part 1, you have to show one-to-one and onto. To show the part 2, you have to show preserves, addition, and scalar multiplication. And really, I can't for doing the homework, you're being exposed to something brand new in almost all cases. You're being exposed to something you've never seen before. Sort of take the how-to out and do, first question, second question, third question, fourth question, until you start saying to yourself, oh, kind of stuff. That's a good feeling. That's the feeling that, this is starting to make the right mental model, the mental schema that fits this part all together. So when you start saying to yourself, oh, I thought this was easy, but it's not actually, I thought this was hard, but it's not actually all that hard. It's actually kind of easy. That's a good spot to be in. That's a very good spot to be in. Okay, so we've gone through a couple of these examples of showing that something is an isomorphism. So I think a person is ready to think about the homework. And next time, of course, we'll go through and look at some more for isomorphisms. Brand new idea. We'll look at some more examples and try to kind of piece it all together and make some sense of what the parts have to say. Okay, very good.